Hello and good day, Algebra. We are going over math packet number 5. Give you some tips and tricks to get you started as you work on it on your own. Note the due date is due 12/18, which is the day before we leave for Christmas break, Friday. So if you're not going to be here that day, then turn it in Thursday or Wednesday or whatever the last day of the week that you will be here. All right. As always, we start with some logic questions here. So it says, in Mr. Bowman's class, 80% of the students eat lunch at school. Of those students, 25% bring their lunch. Of those students, 20% buy their drink. What percent of the total number of students in Mr. Bowman's class bring their lunch and buy their drink? What's important to note here is that every time that we take a percentage, it's not a part of Mr. Bowman's class. Okay? It says that in Mr. Bowman's class, 80% of the students, so that first percentage of 80%, that first one, the whole is Mr. Bowman's class, okay? Let's say Mr. Bowman's class had 100 kids in it. 80% of that would mean that 80 kids eat lunch at school. But then when it says of those students, it's not talking about the original 100. It's talking about those 80, that 80%. So of those 80, 25% bring their lunch. So how many students bring their lunch? Then it says, of those students, so once again, not the original 100, right? But of the students who eat lunch at school and bring their lunch, 20% of those students buy their drink. And then the ultimate question is, what percent of the total number of students in Mr. Bowman's class bring their lunch and buy their drink? So it actually is going to be very beneficial to you to assume that Mr. Bowman's class does have 100 kids in it, okay? Just because the word percent literally means out of 100. So when you're talking about percentages, 100 is a really easy number to work with. So if 80% of 100 eat lunch at school, your first calculation is, what is 80% of 100? Okay? Well, if the word percent means out of 100, 80 out of 100, 80 students are going to eat their lunch at school. Then it says of those students, so now not of 100, but of those 80 students, 25% bring their lunch. So your second calculation is, what's 25% of 80? Right? And you're going to get that number here. Then it says of those students, so not of the 100, not of the 80, but of the number of students that you found in step 2 there, 20% of those students buy their drink. What will that be? Okay, and that final value there, that's not a 0, that's a circle. That final value, you're going to put that over 100, and that's going to represent the percentage of the total students in Mr. Bowman's class who both bring their lunch and buy their drink. Okay? Percentages. Love them. Next logic question. How many rectangles appear in the figure below? I laugh because time after time, students will just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 rectangles. By now you know that I'm not going to give you something quite that simple, okay? The trick here, not really the trick, I shouldn't say that, I'm not trying to trick you, but the key here is to recognize that yes, you do indeed have 15 single rectangles in the figure, right? But how many 2-unit rectangles do you have in the figure? There's one. There's another. There's another. I'm drawing this as neatly as I can so you can kind of see, I'm not trying to overlap too much there, but go through this rectangle and how many 2-unit rectangles are in it. And then how many 3-unit rectangles are in the triangle. And then how many 4-unit rectangles are in the triangle, and so on and so forth. And it should not take you very long to see, oh, okay, this is algebra. What does Mr. Schultz always say? Algebra is essentially about patterns, right? You're going to see a pattern develop here fairly quickly. If this blue stuff is confusing for you, let me kind of draw it in different colors. You know, we have a 2-unit rectangle there. There's one. And then these two in green make another one. And then these two in blue make another one, right? So that's another way to kind of count those 2-unit rectangles throughout the figure, okay? And the answer is, what is the total number of rectangles that appear in the figure? Of course, don't forget to write down why your answer makes sense, whether you just point to your work, you know, say this is what I did here, okay? Or if it's verbal or whatever it is, make sure that you're explaining why you got the answer that you got. 5-card challenge. We're familiar with this by now, I certainly hope. Algebra, you're looking to get 18 points, including at least one 5-card combo. Just make sure that you're using correct order of operations. A great way to check these is exactly what you write down. Put it into your calculator, because your calculator always does the correct order of operations. And so if you put in exactly what you write down and you get 5, then you're right. If you don't get 5, well, then you got to fix it. Probably add parentheses or something like that. All right. Next one. Identify the expressions that are equivalent to the given expression. Defend your decision. So the given expression is 7 times 2x minus 4. Is 9x minus 28 equal to that? Okay. We talked about a couple of different ways that you could attack this, right? You could, one option is to set the two expressions equal to each other and see if you end up with one of those special all real types of solutions, right? Because if 7 times 2x minus 4 is equal to 9x minus 28, then you'll end up with the exact same number of x's and the exact same constant on both sides. Okay, so that's one way to do it. Another way to do it is to just pick a number, plug it into each of them, and see if you get the same result. Okay, that's the second option. Or you can recognize, well, hey, so 9x minus 28, you know, how could I get an expression like that from this one? Well, if I distribute, that's going to get rid of my parentheses. Will that leave me with 9x minus 28? So a couple of different options that you could go there, but you need to defend yes or no why each expression is equivalent to the given one. Next one, we have area, or the shaded area. We've talked about these before. We've got the area of a square, which of course is base times height. I also see a circle here. That area is pi r squared, okay? And just remember here, you know, we're looking for the area of the shaded region, right? These sections out here. So when you find the area of that circle, you're going to want to subtract that from the area of the square, because if you take away what's not shaded, you'll be left with what is shaded. And you've had questions like that before. So anyway, yeah, there you have it. I think that's all we need to say about that one. Next one, the pattern. Your job is to complete the table. And then how many red blocks will be in the 12th figure? That is what you're going to put down right here. Algebra folks, you don't need to do this last line here. That's for geometry only, okay? But you need to fill in the number of blue, red, and total blocks for each figure up through figure 10, and then use that to predict how many red blocks will be in the 12th figure. The first 4 figures are given to you, and so I'm just going to let you take it from there. Okay, get counting, get writing, and get looking for patterns. Get looking for patterns. Next one, we've got a cylinder, and we're looking for the surface area of this cylinder. The surface area of a cylinder. So when we've talked about surface area before, we've said, well, what's the shape going to look like if we kind of unfold it or disassemble it? Okay. Well, if you think of a soup can, that's a great example of a cylinder that you're probably familiar with. If you take apart a soup can, you'll have the top of it. That's a pretty good circle. Yeah. You'll have the bottom of it. Okay, and then that label that wraps around the soup can, if you cut that off, that's actually going to be a rectangle, right? So a cylinder, if you kind of break it down into two-dimensional shapes, it's two circles, one on the top and one on the bottom of a rectangle. So now how do we find the surface area? Well, we're looking for the area of each circles, of each of the circles, and that formula is pi r squared. The radius here is given to you. That's 25. The rectangle is a little bit more challenging. I mean, we can see that this 40, that represents the height of the rectangle, but how do we get this base? How do we get that base of the rectangle? Well, remember that this rectangle represents kind of the label that wraps around the can. And so the base of that rectangle is actually going to be the circumference of our circles, right? The circumference of our circle. So to find that base, you'll be looking for the circumference of that top circle, and that value is going to give you the base of that rectangle. And the formula for the circumference is pi times the diameter. Of course, if the radius is 25, the diameter, which would extend all the way to the other side, is going to be another 25, for a total of 50. And so you can probably take it from here. But yeah, cylinders are, it's if you're not familiar with them, it's kind of like a light bulb. Oh yeah, it's just a rectangle, that label there, and then the relationship between the base of that rectangle and the circumference of the circle. It's kind of like an aha moment there. Next one, we have the volume of a cylinder. Okay, and the formula for the volume of a cylinder, if you've got like one relatively thin pancake, that's like a circle, right? The area of that pancake would be pi times the radius squared. Well, you can think of a cylinder as kind of like a stack of pancakes. The dimension that we're adding to get from a two-dimensional circle to a three-dimensional cylinder is height. Once you start stacking those pancakes, it's just like you're introducing height to the original circle. So the formula for the volume of a cylinder is pi r squared, which is a circle, but then times height. That's the additional dimension here. So the calculation that we'll perform from the volume of this particular cylinder is pi times the radius squared, so 25 squared, times the height, which is going to be 40. Okay? And if I'm going to use the exact value for pi in my calculator here. If you use 3.114, then your volume will be slightly off, but that's okay. Using the exact value of pi, we get 78,539.82, rounding to the nearest hundredth, and our units are in inches, cubic inches. Okay, and for your class, algebra, since you drill a large hole with a diameter of 12 inches down through the center of the cylinder, what is the volume of the part of the cylinder that remains? So imagine taking this, and in the middle of the cylinder, you're drilling a large hole, so all the way up to the top here, you drilled that hole and removed, that entire section there, right from the middle of the cylinder. This has a diameter of 12. I'm looking for what is the volume of the part of the cylinder that remains. Okay, so you've removed that, drilled a hole in the center. What's the volume that remains? Kind of similar to our shaded area questions, right? You're taking away a section of the shape, what is left? Only I don't want the answer as a percentage, I want the actual volume here. Math exploration, ribbon around the earth. Imagine you wrap a ribbon tightly around the center of a large ball, basketball, soccer ball, or whatever. The ball has a diameter of 8 feet, so probably wouldn't be a basketball then. Maybe one of those giant pool balls or something like that. Not pool like shooting pool, but pool like a swimming pool. Anyway, the ball has a diameter of 8 feet. How much ribbon would you need? Show your calculation. So if we're wrapping this ribbon around a large ball, we're essentially looking for the circumference, okay, of that ball. Think about the equator of the Earth, right? Which we're going to get to actually in a little bit here. But we want the circumference of that circle at its widest point. So we would take our diameter of 8 feet, multiply that by pi, and I'm going to use the exact value for pi. We get 25.13. Okay, so we would need 25.13 feet of ribbon to wrap it around that large 8-foot diameter ball. Then it says, how much additional ribbon would you need to raise the ribbon 1 foot away from the ball the whole way around as shown? So imagine this is our 8-foot diameter ball here. We've expanded the ribbon so that it's 1 foot, right? So that's 1 foot. That's 1 foot. It's now 1 foot away from the surface of the ball the whole way around. So it's as if we've increased the diameter from 8, which it was originally. We're adding 1 foot on each side. So essentially we now have a diameter of 10. Okay, so how much additional ribbon would we need? Well, if the diameter is now 10, pi times 10, and again, using the exact value for pi here, is going to be 31.42. The question is how much additional ribbons needed. So if we already need 25.13 feet, we're going to subtract that from 31.42, and that's going to give us how much additional ribbon is needed, 6.29 feet. Okay, now that's just with an 8-foot ball. Imagine wrapping the ribbon tightly around the equator. Okay, so a much larger ball than we had for our 8-foot diameter example here. The diameter of the Earth is 41,804,000 feet. How much ribbon would you need? Show your calculations. Then, how much additional ribbon would you need to raise the ribbon 1 foot away from the Earth the whole way around, just like we did with the large ball? So now we can erase this 181. We can say, you know, this is like the Earth. We have the original diameter, and we're raising it 1 foot, right, the whole way around. How much additional ribbon is going to be needed in order to do that? Okay, and then this last question here, do the results surprise you? Take a minute to collect your thoughts and explain why the results actually make perfect mathematical sense. And the reason why I'm having you show your calculations is that your calculations should aid you in doing that. Okay, ribbon around the Earth. All right, next one. Mean, median, mode. Hopefully you got the memo that you are only doing this for 7 consecutive nights, which if you haven't started yet, then hopefully tonight's Friday. If you start tonight, you'll be done next Thursday, so it'll work out perfectly here. So I'm going to just see 1, 2, 3, 4, 5, 6, 7. We don't need the second half of this here. Okay. You can, if you start tonight, you know, you can put December 11th. And you can round to the nearest 15 minutes. So if you get like 8 hours and 25 minutes, you can round that up to 8.5. If you get 7 hours and 10 minutes, you can round that up to 7.25. It's 0.25 because 15 minutes is a quarter of an hour, right? But then once you get that all filled out, you need to find the mean, median, mode. Oh, this says round nearest half hour, doesn't it? Well, there you go. I guess round nearest half hour. Okay, so we don't need, if you got 7 hours and 10 minutes, you would round that to 7.00. But then it says find the mean, median, mode. It is recommended that teenagers get 9 hours of sleep each night, which is about 38% of your day. What percentage of your 7 days did you spend sleeping? So that's the answer that you put in that slot there. Okay, however many hours total that you got of sleep, what percentage of that 7-day period does that represent? Then we move on to polyaminos. Each of the 10 given polyaminos appears in the figure on the right exactly as they are shown on the left. So no turning, no flipping, no rotating, no any of that stuff. And you need to identify where they are. Just make sure that you're not just, I don't get some that looks like that. I shouldn't have to try hard to figure out where one block begins and the other ends. So if you think, for example, that this one here is right at the top here, just put a line there. If you think this one is right below it, just go like that. Okay. It's easy for me to see where your blocks are. It helps keep it a little bit cleaner. Not all that shading. If you want to use colors, that works awesome as well. Some of you put symbols, that works great too. But if you're just shading, it can be pretty difficult to see where one block begins and another ends. So I believe that wraps up the packet number 5. It is due December 18th. I recommend you turning it in early. It'd be a great thing to do over the weekend. Turn it in Monday. I'll get it corrected as quickly as possible and feedback to you. And it's due on Friday. So that's how you math. Don't forget to like and subscribe. Have a great weekend.